In engineering design, one of the most challenging problems is topology optimization, the process of finding the best possible arrangement of material within a given space to maximize performance, like stiffness or strength, while minimizing weight. For decades, this has been tackled using traditional optimization methods, like finite element analysis combined with iterative algorithms such as SIMP. These are powerful, but they're also slow. A single design iteration can take minutes, even hours, especially at high resolutions. And every time you change the load, the boundary conditions, or the shape of the domain, you have to restart the entire process from scratch. Now imagine a world where you could generate near-optimal structural designs in under a second, on a single GPU, regardless of the shape, resolution, or boundary conditions. That's exactly what we've achieved with Optimize Any Topology, or OAT, the first foundation model for shape and resolution-free structural topology optimization. Deep learning has revolutionized many fields: image generation, language modeling, protein folding. But in engineering design, progress has been limited. Existing deep learning approaches for topology optimization suffer from three critical flaws. First, fixed domain shapes. Most models are trained only on square grids, like 64 times 64 or 256 times 256. They can't handle arbitrary aspect ratios, like a long, narrow beam or a wide, flat plate. Second, fixed resolutions. If you train on 64 times 64, you can't easily scale to 128 times 128, or 512 times 512, without retraining. This breaks the promise of generalization. Third, limited boundary conditions. Many models are trained on only 40-50 predefined configurations, like a single point load at the center and fixed supports at the edges. When you throw in a complex real-world setup, loads in the middle, interior supports, distributed forces, the model fails completely. This lack of generalization isn't just a technical limitation, it's a fundamental barrier to real-world deployment. OAT solves these problems with a novel, end-to-end framework built on three core innovations. First, a resolution and shape-agnostic autoencoder with neural fields. Instead of forcing all designs into a fixed grid, OAT uses a resolution-free autoencoder. The encoder maps any topology, whether 64 times 64, 256 times 256, or a 10:1 aspect ratio, into a fixed-size latent representation. The key is a neural field renderer, a continuous function that reconstructs the design at any resolution from the latent code. This renderer uses a convolutional local image function architecture, which preserves high-frequency details and ensures sharp, binary-like outputs, critical for physical feasibility. Training this autoencoder is clever. We pad and resize variable-size topologies to 256 times 256 for the encoder, then train the decoder and renderer on random patches of the original domain. This enables scalable training and efficient inference. Second, a conditional latent diffusion model. Once we have a fixed-dimensional latent space, we train a conditional latent diffusion model. This is where the generative power comes in. The diffusion model learns to generate optimal topologies by reversing a noise process, starting from random noise and gradually denoising it into a valid design. But unlike standard diffusion models, OAT uses velocity-based denoising and DDIM sampling, which allows deterministic, fast inference in just 20 steps, no need for 1,000+ steps. The model is conditioned on the full problem specification: boundary conditions, applied forces, volume fraction, aspect ratio, and cell size. Third, a new foundation dataset, OpenTO. To train a truly general model, you need a truly general dataset. Enter OpenTO, the largest and first general-purpose topology optimization dataset, with 2.2 million optimized structures. What makes OpenTO special? Fully randomized domains, resolutions from 4096 to 16,384 elements, aspect ratios ranging from 110 to 10:1. Unprecedented boundary condition diversity, over 2 million unique configurations, each with different numbers, locations, and types of supports and loads. Interior forces and constraints. Unlike prior datasets that only apply loads on boundaries, OpenTO includes interior point loads, distributed forces, and internal fixtures. Multiple loads per problem, up to 4,000 applied forces in a single configuration, mimicking real-world complexity. This dataset isn't just big, it's diverse. It's the first to truly capture the full spectrum of engineering problems. We tested OAT on 4 public benchmarks and 2 challenging unseen test sets, using only the OpenTO dataset for training, never on benchmark-specific data. On the 64 times 64 benchmark, OAT achieves 1.74% compliance error, a 32% reduction over the previous state-of-the-art. Even without any post-processing, it outperforms models that use 10 steps of direct optimization. Volume fraction error is just 0.25%, showing precise material usage. On the 256 times 256 benchmark, the gap widens. OAT achieves 1.51% compliance error, while TopODiff scores over 16%. This is critical. High-resolution problems are where traditional methods slow down dramatically. OAT maintains sub-second inference, no slowdown. On the fully general OpenTO benchmark here, that's where OAT truly shines. It achieves less than 10% mean compliance error on problems with fully random boundary conditions, loads, and aspect ratios. Even with a 39% failure rate, defined as compliance over 200% of the optimal. Post-generation refinement with just 5 to 10 steps of SIMP optimization reduces that to under 16%. And here's the kicker. By generating 16 samples per problem, we reduce the failure rate to 16% and compliance error to 1.97%. With 64 samples, it drops to 0.44%. This is the power of generative models. You can afford to generate many candidates and pick the best one. Let's talk practicality. OAT runs in under 0.5 seconds on a single RTX 4090 GPU, from 64 x 64 to 256 x 256, and even for 10:1 aspect ratios. Compare that to SIMP, which takes over 60 seconds at 256 x 256. Even NITO, our closest competitor, scales poorly. At 256 x 256, it's 13 times slower than OAT. And unlike some models that rely on heavy post-optimization, OAT delivers high-quality results without refinement. This isn't just faster, it's practically real-time. Engineers can now explore thousands of design variants in minutes. OAT isn't just a better tool, it's a paradigm shift. For the first time, we have a deep learning model that handles arbitrary domain shapes and aspect ratios, works at any resolution, generalizes to unseen boundary conditions and loads, delivers sub-second inference, and is trained on a large-scale, diverse dataset. This is a true foundation model for structural topology optimization. And it's not limited to stiffness optimization. We've shown that the autoencoder can reconstruct heat-sink topologies, entirely different physics, without retraining, with an IOU of 0.94. This zero-shot capability opens the door to extending OAT to multiphysics problems: thermal, fluid, electromagnetic, and more. Despite its success, OAT isn't perfect. The failure rate on fully random problems is still non-trivial. But here's the good news: failures are fixable. With just a few steps of direct optimization, we can correct the design. And as generative AI evolves, through reinforcement learning, better guidance, or negative data constraints, these failure rates will drop even further. Future work will focus on few-shot fine-tuning for new physics, like stress-constrained or buckling optimization, interactive design where users guide the model via text or sketches, and multi-objective optimization, balancing stiffness, weight, manufacturability, and cost. Topology optimization has long been a bottleneck in engineering design: slow, rigid, and hard to generalize. With OAT, we've broken that bottleneck. We've built the first foundation model that truly optimizes any topology, any shape, any resolution, any loading condition. It's fast, scalable, and generalizable. And we've released the OpenTO dataset, 2 million optimized designs, openly, to spur the next wave of innovation in generative engineering. This is not just a step forward. It's a leap. Because now the future of design isn't just about solving equations. It's about generating solutions at scale in real time.